everyone, good day. We are the Group 5, and today we're going to present to you the paradox of apportionment. So, before I start, let me break down to you what will be our agenda for today. First, the introduction, the description, the definition of terms, the steps and procedures, the sample problems, the interpretation or answer, and of course, our conclusion or generalization and all of the references. So let's get started. So, according to the Article 6, Section 5 of the 1987 Philippine Constitution, our House of Representatives must be apportioned among provinces and cities based on their respective number of inhabitants. It sounds like a simple math problem. More people should mean more sets, right? Now, but in the world of mathematics and political science, simple can get complicated very quickly. This is where we encounter the apportionment of paradox. Mathematically, apportionment is the act of dividing a fixed number of items, like 297 seats, among different groups in a fair proportionate way. We use variables, like the standard quota, to find the perfect balance. However, with the best intentions and the clearest formulas, certain methods leads to paradoxes, mathematical glitches where a province could actually lose a seat even when the total number of seats increases. Today, we're diving into why these mathematical hiccups happen and how they challenge our idea of a fair distribution of power. To start us off, let us look at the basic elements that make up every apportionment problem, to be presented by the next reporter.
Good day, everyone. Before we discuss the different types of apportionment paradoxes, let us first understand what the paradox of apportionment is. So, a paradox is a situation where we follow logical steps and correct calculations, but the results seem surprising or even contradictory to what we expect. In mathematics, paradoxes often appear when a solution is technically correct, but it does not match our sense of fairness or logic. In the context of apportionment, a paradox happens when a fair mathematical method for distributing items, such as seats in government, resources, or representatives, produces results that seem unfair or unusual. Even though mathematical process is correct, the outcome may violate our expectations. For example, a group might lose a seat even though the total number of seats increased. Or a faster growing population might lose representation to a slower growing one. These surprisingly situations are called paradoxes of apportionment. So there are three well-known types of apportionment paradoxes: the Alabama paradox, the population paradox, and the new states paradox. Alabama paradox is an increase in the number of available items causes a group to lose an item. So even though populations remain the same. So population paradox is where group A can lose an item to group B, where the rate of growth of the population of group A is greater than group B. And the new state paradox is the addition of a new group with a corresponding increase in the number of available items. It can cause a change in apportionment of items among the other groups. So understanding these paradoxes is important because we reveal the limitations of a certain apportionment methods. By studying them, mathematicians and policymakers can better understand how to distribute resources or represent more fairly.
The definition of terms. Apportionment. The process of distributing a fixed number of seats among states or groups based on their population. Standard divisor. The number of people that should be represented by one seat, found by dividing the total population with the number of total seats. Quota. The exact number of seats a state should receive, calculated by dividing the state's population by the standard divisor. Lower quota. The whole number part of a state's quota obtained by dropping the decimal. Upper quota. The lower quota plus 1, which is the next possible seat a state may receive. Hamilton's method, largest remainder method. An apportionment method where each state first receives its lower quota and the remaining seats are given to the states with the largest decimal remainders. Apportionment paradox. An unexpected or unfair result that happens when the seat distribution changes in a way that seems illogical. Alabama paradox. A situation where increasing the total number of seats causes a state to lose a seat. Population paradox. A situation where a faster growing state loses a seat to a slower growing state. New state paradox. A situation where adding a new state and new seats changes the seat distribution of the original states even though the population stays the same.
So I am now discussing the steps and procedures of each main paradox. Examples. So the first one is the Alabama paradox. So a little overview about it. Alabama paradox occurs when the increasing total number of seats causes a state to lose a seat even though its population does not change. So here are the steps and procedures. Step number one, list populations of the original states. Step number two, solve the apportionment with the number of seats. Step number three, increase the total of seats by 1. Step number 4, calculate the new standard divisor by having this formula. Standard divisor is equals to the total population divided by the total seats. Step number 5, compute the new standard quotas. By having this formula, quota is equals to the population divided by the standard divisor. Step 6, assign the lower quotas. Step number 7, distribute remaining seats. Step number 8, record the number of seats as the final result. Step number 9, repeat steps 4 to 8 to get the new seat distribution. Step number 10, compare the results. Step 11, after calculating the results, if any state has fewer seats despite the increase of number, that is called the Alabama paradox. So next, I am discussing the population paradox. So a little overview. Population paradox occurs when a state with a faster population growth loses a seat to a state with slower growth. So the steps. Step number 1, record the original populations. Step number 2, calculate the apportionment by using the Hamilton's method. So what are the steps of Hamilton's method? Calculate the standard divisor, calculate standard quotas, assign lower quotas, give remaining seats, and the final apportionment. Step number 3, notice for population changes. Step number 4, keep the same total number of seats. Step number 5, recalculate the apportionment by using also the Hamilton's method. Step number 6, compare the results between the two distributions. And step number 7, even though, for example, seat A grows more than seat B, so seat B might lose a seat. If that happens, that is called the population paradox. To the last example of this paradox, which is the new state paradox, it occurs when adding a new seat changes the seat distribution of the original state even though the population stayed the same. So here are the steps. Step number 1, start with the original states. Step number 2, compute the apportionment by using the Hamilton's method. So here are the steps of the Hamilton's method. For step number 3, add a new state. Step number 4, increase the total number of seats to give a new state at least 1 seat. Step number 5, repeat the apportionment process by using the Hamilton's method. Step number 6, compare the old results to the new results. And step number 7, Even though the population did not change, their numbers of seeds might change, and that is called the new state paradox.
So now I'll be presenting a sample problem with solution. So I will explain the Alabama paradox, which is one of the paradoxes of apportionment. So as we all know by now, apportionment is the process of dividing a fixed number of seats among states or groups based on their population. Normally, we expect that if a total number of seats increases, no state should lose a seat. However, the Alabama paradox shows that sometimes a state can actually lose a seat when more seats are added, which seems unfair or surprising. So let's take a look at a simple example to understand how this happens. So we have here a national council must distribute seats among three states according to their populations. The government uses an apportionment method based on proportional representation. So the populations of the states are shown below. State A with 540 population, State B with 320, State C with 140. So initially, the council has 10 seats to distribute among the states. But later on, the government decides to increase the council to 11 seats. Normally, the total numbers of seats increases. Each state is expected to either gain a seat or keep the same number of seats. However, when the new apportionment is calculated, the unusual situation occurs. One state actually loses a seat even though the total number of seats increased. Now let's proceed to the solution to that problem. So the total population of the three states is 1,000. So we will use the largest remainder method or the Hamilton's method to distribute the seats. So our first case is to distribute the 10 seats. So step one of that is to find the standard divisor since it will tell us how many people each state represents. And to get that is we need to divide the total population and the total seats. That is 1,000 divided by 10, and the equal of that is 100. So this means one seat represents 100 people. Step 2 now is to compute the quotas. We divide each population by the standard divisor. So state A, 540 divided by 100 is 5.40. State B, 320 divided by 100, 3.20. State C, 140 divided by 100 is 1.40. The quota tells us the ideal number of seats each state should receive. Now, the step 3 is to give the whole number seats. We first give each state the whole number part of its quota. We have state A with 5 seats, state B with 3 seats, state C with 1 seat. So since we only gave 9 seats, we still have 1 seat left. And now to our step 4 to give the remaining seat. The remaining seat goes to the state with the largest decimal remainder. We have state A with 0.40, state B with 0.20, state C with 0.40. Since we only have one seat left, even though there are two largest decimal remainder, we will only give it to one of those states. So we give the extra seat to state C. So the final distribution for 10 seats would be state A having 5 seats, state B with 3 seats, state C with 2 seats. Now, let's move on to our second case, which is to distribute 11 seats. So, we increase the total number of seats to 11. Normally, we expect every state to either gain a seat or stay the same, right? But we'll see. Step 1 again is to find the standard divisor, but now it's a new standard divisor since there's a new total seats. So, again, total population 1,000 divided by total seats. Now, 11 equals to 90.91. So this means each seat now represents fewer people, so the quotas will change. So compute the new quotas again. State A 540 divided by 90.91 is 5.94. State B 320 divided by 90.91 is 3.52. And state C 140 divided by 90.91 is 1.54. So step 3 now is to give again the whole number seats. So state A with 5 seats, state B with 3 seats, and state C with 1 seat. Seats given are 9, so there are still 2 seats left. And to distribute the 2 seats left, we go to the step 4, which is to give the remaining seats. We again look at the decimal remainders. We give the 2 seats with the remainders who are the largest. So the 2 largest decimals are A and B, which is A with 0.94 and B with 0.54. So they receive the extra seats. So now the final distribution for 11 seats is State A with 6 seats, State B with 4 seats, and State C with only 1 seat. So if you're wondering when did the Alabama paradox appeared, so to know that, to identify that, we'll look again at the seats of each state during the 10 seats distribution and the 11 seats distribution. We have State A from 5 seats to 6 seats, State B from 3 seats to 4 seats, and State C with from 2 seats to only 1 seat. So even though the total seats increased from 10 to 11, State C lost a seat. This unexpected situation is called the Alabama. To conclude this sample problem, the Alabama paradox shows that in some apportionment methods, increasing the total number of seats can lead to unfair or surprising results where a state may lose representation instead of gaining it.
Hello, I'm Mariah Erin P. de Guzman, and I'll be discussing the interpretation of answer. So, the results of the apportionment show an unusual outcome when the total number of council seats increases from 10 to 11. When there are 10 seats, State A receives 5 seats, State B receives 3 seats, and State C receives 2 seats. When the seats increase to 11, State A receives 6 seats, while State B receives 4 seats, and State C receives 1 seat. Normally, when the total number of seats in a council increases, each state should either gain a seat or keep the same number of seats. However, in this case, State C loses a seat going from 2 seats to 1 seat, even though the total number of seats increased. So again, this situation demonstrates the Alabama paradox, which occurs when increasing the total number of seats in an apportionment causes a state to lose a seat instead of gaining or keeping the same number. This paradox highlights a limitation of Hamilton's method and is one reason why other apportionment methods are sometimes preferred.
To conclude, the paradox of apportionment demonstrated that achieving perfect fairness in distribution is not always possible. Even when mathematical formulas are used to divide representation proportionally, unexpected outcomes can still occur. These paradoxes highlight the limitations of different apportionment methods and show that no single system is completely flawless. By studying the paradox of apportionment, we gain a deeper understanding of the challenges involved in fairly allocating representation in governments and organizations. Ultimately, mathematics helps us guide decision making, but it also reveals the complexities behind what we consider fair.